Are we more or less ready? Nobody outside? Did you see anybody outside?
No.
Check this. Okay.
Oh, I see.
You working?
Just one day.
Yeah.
Are we rolling or?
Yes.
We're rolling. Okay.
Okay. Okay, it works. Yeah.
Okay, so hello everyone, we're back, and today Hanqing, sorry, will tell us about local symmetric quantum system and Liu conservation.
Okay, thanks for the introduction. I really appreciate all the effort made by the organizer, and thanks everyone who's still being here for the last day of in-person talk. Yeah. First, I want to apologize that I will not talk about QFT in this talk. So this problem is originally motivated from quantum information, but we believe it could have much more applications to possibly quantum field theory. So if you can see any application, please let me know. So I will focus on the local symmetric quantum system. So before I start, I want to, because locality and the symmetry are very important in this work, so I want to carefully define them. So symmetry here just means global symmetry. And the locality here, so for example, if I say two local, it actually means a two-body interaction. So that means it's a Hamiltonian which only acts on two sides at a time, but we don't require any geometry of the lattice. For example, we consider systems on some lattice sites, so they can be arbitrary lattice sites. And the interaction can be far away, like between this one and that one. But since we don't require geometry, we still call it a two-local Hamiltonian. So I'm just clarifying what I mean when I say two-local Hamiltonian. So it's actually, you can think of it as a two-body interaction or something like that.
Two local.
Two local, yeah. Two local. There are also three local.
It's not too much local.
Oh, I see. There are also, nice clarification, yeah. There are also three local, four local. That means the Hamiltonian simultaneously act on at most three sides, four sides, etc. So in this work, we will focus on the simplest non-trivial case where it's between two sides. Okay, so yeah, I can use this. So this work was done together with Professor Imam Marweh from Duke University and his grad student. Yeah, so our work is basically based on, as I said, symmetry and the locality. So we know that symmetry, it will imply the Euro conservation laws or the Noether's theorem. But locality itself, it doesn't impose any conservation laws for a thing as a quantum spin system, etc. At least, so and it was shown long ago in this paper. So the question we want to ask is a very simple question. So it's just if our system has some symmetry, together with symmetry, can locality lead to new conservation laws, which are not captured by Noether's theorem. So I think our problem is quite simple, but I'm not sure whether is there any question about this?
Actually, can I ask already on?
Yeah.
I had thought that actually symmetry plus locality is required to get a conservation law. But I think you're saying that's not true. You're saying symmetry alone, even in a non-local system, will give you a...
So I think that depends on what we mean by these conservation laws. So I think maybe you are thinking usually the Noether's theorem in the field theory, right?
Yeah.
And we consider local interactions.
Yeah.
Here we are using this in a slightly different sense. So just think of a spin half system, and it has SU2 symmetry.
Yeah.
Then so this might not be the Euro sense people use this word Noether's theorem. Here we just mean if a spin chain with SU2 symmetry, then the total spin is conserved like this, right? And the spin in x direction, y, z direction, they're all conserved. So I just mean regardless of locality. Yeah.
There's no current.
There's no current.
There's no current.
There's no current, just the charge. Is that the right?
Just a charge. Yes.
Okay, okay.
Yes. No current. Yeah. That's a good point.
Okay, thank you.
Yeah. Okay. Yeah. So. Yeah. So it was recently shown that locality, it can indeed restrict the long-term dynamics of a system. And in particular in our work, we will show that two local or two-body Hamiltonians with SUD and D greater or equal than 3 symmetry, even you consider a pure state, which is constrained in one ERAP or one charge sector, it can have new conservation laws that are not captured by the Noether theorem in the sense I just explained. So, and there are two types of conservation laws. One is based on a Z2 antilinear symmetry. The other is based on Mach2 free fermions, and this is basically what I will explain later. And there are many possible applications. For example, it can apply to SPD physics, where by definition symmetry and locality are both important, and it can also apply to quantum complexity, quantum chaos in the presence of conserved charges. So these are possible applications we could think of. So
when you said that non-Noether theorems means that it's because they do not lead to unitaries, or because they just don't follow reference?
no, sorry, can I say that
Well,
again?
when you said, well, can you clarify what you mean that they don't follow by Noether theorem?
So it's just some by Noether's theorem, some interactions would be allowed, but actually they are not allowed if you require locality. And our new conservation law will capture this new constraint. Yeah, that's what I mean. So yeah, so I think it will be more clear as we go. So before I start, let's look at a simple 6 Q-trait example, where Q-trait simply means its local hyperspace is 3-dimensional, and they can be labeled with 0, 1, 2, these 3 labels. So the hyperspace is just a C3 tensor power 6, and the singlet is defined on 3 sides, which is the totally antisymmetric states on 3 sides. And then we consider 6 Q-traits. The first 3 are in a tensor product of 0 state, and second 3 are in the singlet state. So we choose this state because it is inside a single ERAP sector of the SU3 symmetry, which is a strong requirement, and we want to consider the state transition from this state I described here to a linear combination of the original state and the state with these 2, 3 swap. So it turns out that if we have generic SU3 invariant unitaries, this state transition is possible for arbitrary theta, and it can be realized concretely using this unitary, where this P14 is the swap Hamiltonian which changed the first and the fourth side, and similarly for the other ones. However, this Hamiltonian here, it simultaneously acts on 6 sides. So it says local, but it's not too local by our definition. So what if we further require we only allow Hamiltonians to be too local? Then this state transition is not possible unless theta equal to 0 or pi, because we figure out a conserved quantity associated with this state and this operator. So it's only conserved when theta equal to 0 or pi. So that's a simple example. Is there any question here?
And that's no matter how many such two local gates you apply.
Yes. So and it can be arbitrary. It can be time dependent. Yeah. The most generic two local gates you can think of. Yes. So this is always not possible. So like you can go from this state to some state with arbitrary theta, but if you require your unitaries to be restricted to a plane where spanned by two locals, then there is not a path from this state to a generic theta state. There is only a path if you leave the two local plane.
Sorry, there was, I mean, maybe I missed the point, but you're only considering evolution, the local Hamiltonian solution of this particular state, zero, three zeros and a single.
This is just an example, yes.
But well, I guess what I don't understand is that theta is a particular quantity of evolutions of that state. Like, it's not a quantity of a system, and you're saying this is a conserved quantity. So how do I interpret theta
No.
as a quantity of a system?
So you can think maybe one way to think of this. You can think of this theta as a just a parameter of a class of states defined by this way.
Uh-huh.
So that's one way.
But that's not exhaustive, right? I mean, there are other states.
There are other states. I'm just giving some very simple examples. So you are your original state is somewhere here, and from this state, evolved by that unitary operator, you can evolve to some state parameterized by theta, right? And any theta is possible if we, so any of these states are possible because you have a unitary to go, SU3 invariant unitary to go from a state here to any state on this line. However, if you require two local, then maybe a better way to draw it is like
There's markers in the board.
yeah, I mean the eraser.
Oh, eraser. It's on
Behind.
the table.
Oh, I see. Thank you. I think a better way to think is that you start with some state, and there is a plane which are states you can reach by two local unitaries. These are states you can reach by two local unitaries, and we also consider a class of states parameterized by this. This class of states actually leaves all set of this plane except theta equal to 0, which you are oriented here, and theta equal to pi. So, so why these states are not possible? Because basically this is a quantity which you can associate to a state. So the generic form of the quantity is not of this form. Yeah, I think that might be the confusion. A generic state, it has some other form. It's only of this form for this class of states.
Okay,
So and that generic quantity, they are conserved on this plane.
I see, so there is some quantity which for a general state you're saying is conserved, it's just not.
Yes, some quantity for general state is conserved. And for this class of state, it's of this form.
Okay.
Yeah, thanks for the.
What is the nature of this quantity? Just a number that doesn't change
What's,
or what?
what's the nature of this quantity? Yeah, that's a good question. So later we will see it's related to the single particle reduced entropy. So yeah, we will later see how we define. Yeah, thanks. This is a very good point. I think it was confusing. Yeah. So then let's talk about the setup of our system. Yeah, just formulate it. So the Hilbert space is n copies of d-dimensional local Hilbert space, where it's just a c power d to the tensor power n. And the Hamiltonians we consider as global SUD symmetry. That means Hamiltonian commute with u to the tensor power n, where u is a arbitrary element in the SUD. So now let's consider what's the consequence of symmetry, or the consequence from like what I mean by the Noether's theorem. So this Hilbert space forms a representation of the SUD symmetry, and it's decomposed into EREFs of the SUD symmetry. However, each EREF, so this lambda labels the EREFs. And this Q lambda is a EREF space, but each EREF has some multiplicity, which is denoted by this M lambda. So in a simple case of D equal to 2 in SU2 symmetry, lambda is just angular momentum. So in general, it can be the general Casimir operators. So then we consider what are all the Hamiltonians which has this symmetry. So by short lemma, we know it must act block diagonal in this decomposition. It cannot mix sectors with different angular momentum, for example. Furthermore, using short lemma again, so it must act as identity on this Q lambda space, because this is an EREF of SUD, and it should commute with SUD action. However, it can be arbitrary on this multiplicity space. And by short value duality, we know actually this lambda, in general, we can draw Young diagrams for them. They label both SUD symmetry, so they label the EREFs of both SUD and the symmetric group. And we also know that all the Hamiltonians, which has SUD symmetry, can also be written as a linear combination of permutation operators. The sigma is a permutation, and the p is an operator acting on the Hilbert space. So now let's look at the consequence of locality. Basically, we already know all the Hamiltonians are basically permutations. So two-body interactions or two local Hamiltonians, they are just associated with two cycles. And we call these permutation operators as swap operators. And the Hamiltonian is just a linear combination of swap operators. So for SU2, up to a identity, this Hamiltonian is basically the Heisenberg interaction. We allow interaction between any sets. So more generally, we can also include all terms in the Lie algebra generated by these operators. And they look non-local, but we still consider them as two local because they will always be generated by two local Hamiltonians. Yeah, and we will refer to all these Hamiltonians in the Lie algebra as two local Hamiltonians. So, and if you look at the 6 Q-trait example again, so it decomposes into EREFs labeled by these Young diagrams. Only 5. Oh, 10, I see. Thank you. We can check the dimension of all the SU3 invariant unitaries and the dimension of two of SU3 invariant unitaries, and this is much less. So that means there are other, possibly other conservation laws we didn't see from the Noether theorem. So first, let's look at the Z2 symmetry. So let's first get some intuition of this Z2 symmetry. This is because if you look at the product of two local unitaries, we can expand them, and we see so these are even permutations, 1 and this term. Their coefficients are real, while all the odd permutations, their coefficients are imaginary. And we can also see this in terms of Hamiltonians, where I will also put an additional I to make it anti-Hermitian. So P is Hermitian, so we put an I. So that means the swap operator, it should be imaginary. And if you take a commutator, it becomes real, and this also becomes a even permutation. So this pattern holds in general. All the operators generated by these swap Hamiltonians, if they are even, then the coefficients are real. If they are odd, then the coefficients are imaginary. So if you know the little bit about representation theory of the symmetric group, these actually have constraints for, just draw two simple Young diagrams. This is one EREF sector, this is another EREF sector. So as representation of the permutation group, so this representation is actually this representation tensor with the sign representation. Therefore, if you have a even term acting on this space, it also acts same way on this EREF space. And if you have an odd term, it got a minus sign on this space. Therefore, if you don't require any reality of the coefficients, these two sectors are completely independent. However, if we require, as we see from the pattern, all the even should be real, while all the odd part should be imaginary. Then this becomes a complex conjugate of that. So then these two sectors are no longer independent. They become the dual representation of each other. So yeah, there's some more comment on this. So, and then we figure out a conservation law associated with this Z2 symmetry. I wouldn't have time to discuss about it, but it's little bit peculiar because it's not quadratic in the state as Euro symmetry. It's a quartic in the state. And we do some numerical simulation to confirm this. So we start with a state, this state which restricts into this EREF. So because this diagram, it is symmetric when you exchange column with row. Therefore, it preserves some. So therefore, the representation there is self-dual. So it preserves some bilinear form. So therefore, it has some non-trivial constraint on this sector. And we first just use the two local Hamiltonians. We indeed see it's conserved. So, and in this plot, we use both periodic two local Hamiltonian and random two local, so they don't make a difference. So, and then we turn on the three local interaction which violates the Z2 symmetry. Then the quantity is no longer conserved. Then we turn off the three local interaction and then turn on a four local interaction, which is not turn out to be not too local. but it still satisfies the Z2 symmetry. Therefore, they are still conserved. Therefore, this quantity characterizes the Z2 symmetry. However, here, as I said, it satisfies the Z2 symmetry, but it's not too local. It's still conserved. That means there are some other constraints we didn't include to characterize to exclude these terms which are not too local.
Sorry, I didn't get the y-axis.
Oh, the y-axis is the conserved quantity I.
See, this is what you.
Yeah, this is a conserved quantity I. Yeah. Yeah, thanks for clarification. So.
Can I see the conserved quantity?
So yeah, I removed the definition of K because I think I don't have enough. But you can read. But you can read from this.
Yeah, you take the state.
Yeah. You basically need to think of two copies of the state, and since here they are sort of related to the constraints in these two sectors, which are related to a sign representation. So that's why we need to put a sign representation. Yeah. Yeah, there are some technical details here, but I just want to show you there is one, and this Z2 symmetry is I think it's very peculiar. We think it doesn't have a unitary or anti-unitary representation on the Hilbert space, but it is antilinear on the operators. It is an antilinear operator, but it's also anti-commute with the Hamiltonian. So it is a symmetry of the Hamiltonian, but it's not a time reversal, although it's antilinear.
But if you combine it with time reversal time this, then it will be a linear. So you want out the time reversal.
That's a good question. So it's only true like in the particular system we are talking about. That it turns out there is a symmetry which is antilinear and anti-commute with the Hamiltonian. So which usually is supposed to be bad because it will flip the spectrum. But we are thinking some finite dimensional Hilbert space, so we still allow symmetry to anti-commute with the Hamiltonian.
Is there time reversal in the usual time reversal in your system? Or no?
Is there a Euro time reversal? I think Euro time reversal.
I guess you're right, this is not time reversal because it doesn't reverse time. It reverses the I in front of the revolution operator and it flips H.
Yes.
And
So.
that's an invariance
Yeah.
of the time evolution operator.
Yeah, and in our case, all the even permutations are real and odd permutations are imaginary. So if you just do an anti-unitary or antilinear transformation, it's not a symmetry because it's only flip the odd part. It doesn't flip the even part. So yeah, that's a good question. I have to think what's the Euro time reversal symmetry. Probably it just doesn't have that symmetry. I don't know. So we need to have more constraints to have that symmetry. Yeah, let me, okay, I'm almost running out of time, but just want to quickly explain the second type of conservation law is basically map subsectors of the system to a fermionic system. The mapping basically works as follows. We map these states, we view these states as one particle, one fermion state, and this is like a two fermion states, etc. So and think of always permutative versions. Then we can map these subsectors to a fermionic system. Then the observation is that for the swap Hamiltonians, for fermions, they are all free. So these are all the Euro definition of the fermionic operator and the Fock vacuum. And the swap operator is defined as literally swap these creation operators. And we further require the vacuum to be, the Fock vacuum, to be computationally invariant. Then there is a unique representation of this swap operator in terms of CNC dagger. and it is quadratic. Therefore, the swap Hamiltonian are all free, and if we look at the unitary acting on these creation operators, it just form a Bogoliubov transformation of these operators. So, and because they are free, we can construct many conserved quantities, and one particular one is to look at a single particle reduced state, and then calculate its linear entropy. And on the next slide, I will focus on the second linear entropy, which also you will call the purity of the state. So in this case, we consider a state restricted in the fermionic sector. All the fermionic sector, their Young diagram looks like an L shape. So we calculate this quantity, and if it's the Hamiltonian, if it's 2 local, it's conserved. If it's 3 local and not in the Lie algebra generated by 2 locals, it's no longer conserved. And furthermore, although we put a Hamiltonian which satisfies the Z2 symmetry, but it's not 2 local, but this is the same Hamiltonian we saw before. It satisfies the Z2 symmetry, but it's not 2 local. Therefore, this conserved quantity captures the consequence of 2 locality, because this quantity is not conserved for this unitary. Yeah. So I think that's pretty much what I wanted to say. So in presence of symmetry, we found locality impose additional conservation laws. One is related to Z2 symmetry, one is related to a fermionic system. And these conservation laws are actually broken by generic three-body interactions. They are no longer hold. And since our problem is basically think of the Lie algebra generated by permutations, and the Lie algebra is also, the permutations is also Z2 graded. We also think about what's the Lie superalgebra generated by them, and but we haven't think of a physical application of this. So yeah, so that's one. Yeah. So with that, I think thanks for
We are a little bit over time because some more people asked questions. But maybe we have time for one question, and then you can discuss in the break if somebody has a question.
If we further restricted and looked at only nearest neighbor interactions, so local and unknown.
That's a good question. So actually, whether it's nearest neighbor or not, it doesn't make a difference. That is because if you look at this Hamiltonian, and you choose, I think, so basically if you expand this, you choose some theta. This can be just a p, I think it's theta equal to pi. It is just a p1, 2 with up to some phase. So that you have all the, then you can compose different unitaries, p2, 3, etc. Then you can have all the permutations as unitaries, not as Hamiltonians. Then using these unitaries, you can move your sets around arbitrarily. So yeah, although they are not local, you can always using 2 locals to move 2 sides next to each other. So there is no further thing we gain by requiring